So we're going to start this with the idea that the net force is equal to 0. Now, that assumes it's 0 in every direction. We're going to assign direction to this problem, but no matter what we assign, it's going to be balanced no matter what direction we're thinking of. Now, when I start thinking about the forces on this, I'm going to draw each force in the order that I discover it. And what we're doing is we're starting to draw our pictures just based on what we saw the last time. I can definitely change that and make that harder for you by giving you a situation you've never seen. So please, start at the beginning. Is there any fundamental force acting on the box? The answer is yes, and I think that you're probably right. Then let's draw that fundamental force. In this case, it's weight, and that should be drawn as a single arrow downwards. Now, when we start drawing these forces in, oops, didn't want to do that. When we start drawing these forces in, one of the things I want you to be kind of thinking about in the back of your mind is, if this is balanced, then I need to be considering how big each of these forces should be. So if this is the weight of the object, I'm kind of setting the scale for everything else by the length of that arrow. So I'm going to write W at the bottom so we know it's weight. And then I'm going to start going through contact forces. Is the box in contact with anything? It's in contact with the ramp. So there's two different kinds of contact forces. There's tension and normal force. Which one are we looking at here with the ramp? All right, so that's going to be a force drawn perpendicular to the surface. I mean, that's what we mean when we say normal, that it's perpendicular to the surface. That's why I'm drawing it that way. And it's not because, I know something you don't. I have to follow the rule, which is normal forces are always pushing forces, and they push away from the surface. So I'm trying to be careful to draw that to indicate it's in the same direction as away from the surface is in my picture. And I'll label it N for normal. Now there's other forces acting because those two aren't balanced, right? They don't look balanced to me. It looks like the object would go off this way if I was just to let it go, because they're kind of both pulling that way. So I need to find, another force that's acting here, and there's no cables connected to the box, so there's no tension. So then I go to resistive forces. Are there any resistive forces acting in this system? And the answer is, yeah, I think so. I think there's going to be friction acting in this system. Now, it doesn't matter what the situation is, friction has to be parallel to the surface, period. Now, that means it could be, parallel could be this way, and parallel could be, this way. Friction could act in either one of these directions. It depends on what's happening at the time. If I was pushing the box up the ramp, then friction would be acting this way. But if the box were sliding down the ramp, friction would act this way. Now, neither of those circumstances are happening right now. The box is just sitting there. What direction do you think friction would have to be for the box to just sit there? A or B? Guys at home, A or B? Which direction? Yeah, I think so too. So in drawing this force, I'm going to draw an arrow. Well, I didn't want it to be that big. No, that was not my goal. An arrow this way. And I'm not going to draw it very big because I don't think it has to be very big. The reason I'm saying that is, look, the way these are unbalanced here, I just need a little bit to hold it in place. But I do want to make sure that these are drawn perpendicular to each other. So that's your free body diagram, and the only other thing I would ask you to do here is decide on a coordinate system. Now, it doesn't matter what your coordinate system actually is. I could put the coordinate system like this. I could do it like that. It would make the problem harder because I have two forces that aren't on the coordinates. That would be the hardest way to do this problem. And it wouldn't make any sense. So when you choose a coordinate system, you're trying to choose something that's going to make the problem easier. And that's why we've talked about the fact that we want to kind of turn the coordinate system to line up with the normal force. If we do so, then it also automatically lines up with the frictional force because they are perpendicular to each other. And this is why we turn it this way. Also, if we do that, it's incumbent on you to know that this is where the 35 goes. Now, so far when I looked at a lot of papers, I saw this, but then I also saw this on like 4 papers. 3 of them at home and, well, I guess it was a couple in class. People who drew this next. This is a common problem I see all the time. And I can guarantee you'll get lots of stuff wrong if you do this. When you're drawing your components, you are wrapping a right triangle around your angle. It has to be a right triangle, but that doesn't mean that the right angle is over here. It's not. Your components, they have to be at a right angle to each other. So I draw this side first, and I try to stop it when it's level with the other one, so that a right angle exists here against the axis. That's your right triangle. And moreover, this side here is how much of the force is going down the ramp. And this side here is how much of that force is going into the ramp. This part is what's pulling it down. That's the part that's going to determine how fast it slides down the ramp if there's no friction. It's also what you would have to work against if you wanted to push the box up the ramp, which is why ramps do what they do. It allows us to have less force to move something up. So when we break these up, we're still going to use our rules for triangles, still cosine and sine. This is the adjacent side, and this is the opposite side. So because this is the adjacent side, this one will be mg cosine theta. And because the other one's the opposite side, it'll be mg sine theta. Now I said yesterday you could just commit those to memory, and that would be fine. The problem is that I've drawn all my components now on my actual diagram that I have to use for grading purposes. Tomorrow's test, you won't be able to do that. But I do want, yes ma'am.
How much should we draw on our diagram?
If you want full credit,
Should we put in angles?
if you want full credit, that's all you have to draw. Putting the angle in here, that would be good too. But that should be it for full credit on your
Substitute the W here.
you can do that, that's fine. All right, so
Wait, so if we put the angle on the free body diagram, we won't have points taken off, right? If we put the angle?
right, you will not have points taken off if you put the angle on your free body diagram.
Okay.
You'll only get points taken off if you start putting the components on there. That's when you have points taken off. Because it's going to state, do not put components on your free body diagram. So you need to have another diagram off to the side, something that you might work from. You know, that's what I'm kind of doing now. My diagram off to the side. I don't have to be as careful. This is the one I'm working from. You know, I know I'm going to have normal force, mg sine theta, friction, and mg cosine theta. I've just put the components right in there. Aaron has more fun in my class than anybody else. I never see anybody smiling more than Aaron. I don't know why.
You can't see us smiling.
I can't see any of you smiling. That's true. That's true. You're all hidden. Aaron's having the best time up there. So the net force equals 0. And I don't know if you guys recognize this, but I'm going deliberately really, really slow. And that's not accidental. It's to try and make sure that the people who are having trouble with this are kind of catching up. You guys who are catching on to this, great. But there's a few of you that really are having trouble. And I'm trying to be deliberate so that you have either a chance to catch up or a chance to get your question in edgewise. Like I just had a kid come in this morning to drop the class. You know, and it's heartbreaking, but I'm not going to try and convince people to stay. At the same time, they never asked one question in the last 6 weeks. That's tough. You know, and I know these circumstances make it hard. So at this point, I said that the net force is equal to 0, so I'm going to break that up into 2 directions. Net force in the x direction is equal to 0, and net force in the y direction is equal to 0. Now the result of this, you shouldn't assume is always going to be true. This can change, and it's going to change on the very next example we're going to do. But for this one, it is true that I have mg sine theta down the ramp and friction up the ramp. Those have to sum to be equal to 0. Why? Because it's not accelerating. And I have mg cosine theta into the ramp. I'm going to make that negative. And normal force up the ramp. Those have to sum to be equal to 0. Now, a lot of you guys like to dump your numbers in there nice and early. Fine. If you've got, 50 times the sine of 35 and you know what that number is and you want to put it in there from the very beginning, fine. Do so. I don't. But that's something you might want to do. Now, once we get here, we're really done. There's not a whole lot to do. So let's take a look at what I would more expect to see you do on the test. So when it comes to test level question, what I'm expecting you guys to do is more like this. Still, box on a ramp. But this time, give me an angle between 30 and 50, not 45. 43. I'm going to say no. I'm going to pick for you now. 43 is too close to 45. You're never going to get 45 on the test on purpose because sine and cosine of 45 are the same. So we'll say 50. That's what I want. Something that's bold and different. And I'm going to have a person pushing the box up the ramp. The box is accelerating up the ramp with an acceleration of 2 meters per second squared. So they're pushing on the box and it's accelerating. Now, if you want just the basic for the test, I want to know how hard they're pushing. Assume they push parallel to the ramp. Okay? So the basic question is how much pushing force is there? Give me a mass of the box. How many?
20.
All right, so it's a 20 kilogram box. Now, if you want the full question, one that might get you, an A on the test or maybe a little extra credit, add this sentence. If you're getting this and you feel confident, you should add that sentence to your question. If you're not getting this, you shouldn't. But adding that question is what it'll take to get an A on the test. Okay? Any questions about what I'm asking you to do? let's take a few minutes on this, maybe 5 to 10. You guys at home, I'm gonna put you guys into breakout rooms to have a chance to kind of talk it out with somebody. And I'll jump into the breakout rooms. It's easier for me to help you out that way.
The recording has stopped.
Ouch. There you go. Why don't you jump into those breakout rooms? And I'll pop in there and answer your questions in there. The idea of them having breakout rooms so they can talk to each other. You guys are welcome to work together if you want to look around and ask each other questions. Well, I want to be careful when I say that. It doesn't matter, except that If you labeled up the ramp negative, then your acceleration had to be made negative. You gotta be consistent. How are you guys doing in here?
Mr. Shelton, I have a question about the angle.
Okay.
Okay, so right now, alright, let me turn my camera real quick, so I can see it. I'm not sure if you can see it, but right here,
Uh-huh.
I'm not sure if the angle is supposed to go in this corner or if it's supposed to go in this corner right here.
Okay, so I think it's an excellent question. I'm going to draw it here on mine. If you make, say, this way your y-axis, okay, I mean, it doesn't matter what you label it, but the one that's perpendicular to the ramp compared with the weight of the box. So if this is the weight of the box, the angle goes between those two. Okay? You're welcome. Is there any other questions before I jump into one of the other rooms? All right. This problem's tough. I'm seeing a lot of mistakes in this classroom, so we're going to start talking about it here in just a minute. Hey guys, I'm just jumping in. How you guys doing? Okay. Did you guys choose to do the one with friction or without? Okay. Well, good luck then. I'm probably going to close up the rooms in about a minute or so, okay? You guys have any questions? I guess not. Okay. I'm probably going to close the rooms in a minute or so, okay? All right, we're gonna start talking about this problem again, guys. Having looked at your work in the room and a little bit of what I'm seeing at home, there's a lot happening that is going to lead you into problems on the test tomorrow. So let's kind of come back together here and see, I've got a few more folks that are coming back from the rooms, but there's several things that are missing from the bigger picture here that I really need to kind of emphasize. The first one is that the box is accelerating. I had a few folks who had difficulty understanding what do we do with that now? Well, that means that the net force equals ma. The acceleration doesn't go on your picture anywhere, but you do have to take into account the acceleration of the system because all of these forces are going to add up so that the net force equals ma. And what that really means is the net force equals 20 times 2. So it's 40 newtons is the net force. And what direction do you think the box is going to accelerate? And I kind of drew it into the picture, but what's suggested there is that there should be more force up the ramp than there is down the ramp. And it's definitely not accelerating in, say, this direction or this direction. So when we start looking at the forces acting on the system, we need to be aware of all the things that might be pulling it up or down the ramp in order to determine how much force you have to push with to make this happen. So let's talk about the forces that are acting in the system first. We'll do it over here out of the way. We have at least 3 forces. If you did the more advanced problem, you might have more. But we'll start with weight. And that one's pretty straightforward, pretty easy to deal with, and it's a 20 kilogram box, so the weight is 200 newtons. Now, the box is in contact with the ramp, so there's a normal force. And the normal force should be drawn so that it is heading away from the ramp, perpendicular and away from the ramp. A lot of you guys in drawing your pictures aren't really being very careful, and that's going to make this harder. So you might want, before you even start, drawing your picture, you might want to consider, okay, this is now my y-axis. I'm going to kind of put it out here so I can keep that in mind. And my x-axis has to be perpendicular to that. And try and make those kind of adjustments earlier rather than later. Because a lot of you guys, you have these lines that are like this for your axes, and that's going to start making this harder for you to see what's happening. All right. So if you're not doing the problem with friction, the only other force you have to add now is the pushing force of the person. They have to push up the ramp in such a way that they are pushing harder than the weight of the box going down the ramp. And you don't have to do anything funky with the name. You can just write in the word push. That's fine. This is a force that's given to you in the problem. If you had friction, if you wanted to do the frictional part, that's fine. But a lot of you are having difficulty figuring out what direction forces go. And you're just drawing them because you think there needs to be something in a certain direction. But friction opposes the motion of the box. So if you chose to add friction to this problem and make the problem the harder version, then your friction needs to be in opposition of the way the box is moving. The box is moving up the ramp, so friction would have to be drawn down the ramp. It opposes motion. So these are the forces that act in the system. And on a free body diagram, that's what it should look like. Any question about any of these? Well, let's handle the weight. Although it's 200 newtons, this is my 50 degrees right here. Had some questions about where to put the 50. It goes between the perpendicular axis and the weight. You may want to emphasize that in your notes. And I know there's a lot to keep track of. I get that part. But now I'm going to, and again, this should be done separately somewhere on your work. I'm going to draw the component that's in the y-axis first, because that's where the angle is. And I'm going to stop when it gets kind of level with that. And I'm going to turn and draw a perpendicular outwards so that this is 200 cosine 50 degrees, and this is 200 sine 50 degrees. Questions about what I've drawn so far? All right. This is just to be used to help us solve the question. So now that I've done all that, some people actually say, okay, I've done all the hard parts. I am going to turn this and draw everything so that it's kind of level for me because I'm having a hard time tilting my head and seeing this. So there's nothing wrong with saying, okay, now I've got it drawn out. This is normal. This is 200 cos 50. This is friction, and there's 200 sine 50. And this is me pushing. Those are all the things that are happening. I stack the arrows here instead of drawing them side by side. It's just a different way of doing it. Stacking them gives you the impression that you have the length of the arrow as how big the total force is in that direction. But there's two that act that way. Now, I don't know what you made positive and what you made negative, but I've encouraged you to make the positive x direction the direction that it's accelerating. Somebody in the classroom asked, can I make any direction negative? Sure. But if you made the direction the box accelerates negative, you also have to make the acceleration negative. You'll have to make that number negative because that's the direction it's accelerating. So I would encourage you, so that you can be consistent, just make the direction it accelerates positive. You'll have less trouble. And this is the positive y direction. Now, the net force in the y direction equals 0. The box doesn't move into the plane or come away from the plane. So that tells me that the normal force minus 200 cosine 50 equals 0. But I'm running out of space, so there. The net force in the x direction, it equals ma. And there's quite a few things I have to put here. There's the pushing force, that's in the positive direction. There's the frictional force, that's in the negative direction. There's 200 sine 50, that's in the negative direction. And that all has to equal ma. Now, if you chose to do the basic problem, you don't have this. But if you chose to do the more difficult question, you do. And before you can go on, you need to find out how big that is. It's 20% of the normal force. So you need the normal force first. Yes, ma'am.
Is the friction always 20% of the normal force?
No, but it's always a percentage of the normal force.
Will that be stated in the problem?
Or you'll be asked to find it. We've been not dealing with that part yet. I'm just slowly introducing what friction is and how it works. So let's find out how big the frictional force is.
Good morning, teachers and students. It is time for morning announcements. Please stand for the pledge.
Pledge time.
I pledge
Allegiance to the flag, United States of America, and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Thank you. May be seated. Attention students, the Mu Alpha Theta Math Honor Society will be accepting applications for new members from Tuesday, October 6th through tomorrow, October 9th. If you'd like to see what the criteria are for membership and then fill out an application, please see the link on the Canvas dashboard. Again, the deadline to fill out an application is this Friday, October 9th. There will be a girls' basketball meeting Tuesday, October 13th, after school in room 605. If you have any questions, you can see Coach Key in room 605. Tryouts are going to start October 26th in the gym at 3 o'clock. And make sure that you have all your paperwork completed to try out. You can find all that information on the Signals website if you click athletics. Teachers, please be aware that there's a time change for the golf match today. So any golfers will actually be released at the end of fifth period today. And there is an email to back that up on internal. Thank you. And our menu for today in the cafeteria: assorted pizza slice and grilled cheese sandwich. Also, the hot bar will be the potato bar today. All right, thank you everybody. Have a great day.
All right, I just continued on so that we can finish. And I think I'm almost done. So I found my 20% of the normal force, found my normal force, and I put all of these pieces together. And I don't know what this is going to be, but I have to do some adding to get that. Looks like it's 40 plus 153 plus 25.7. So I find the pushing force was like 219 newtons. Good yawn there, Anthony. Good one. Solid yawn. I appreciate it. So I believe that we're probably not